All right, so we're going to start talking about things called polar coordinates. Okay, one of the benefits of polar coordinates eventually is going to be in the fact that it expedites some algebra for us. Okay, it makes some things a little bit easier for us to do in regards to working with complex numbers, especially. Okay, but it's just a different way of doing things. There's other things called parametric equations that might be a little bit easier to deal with in regards to using polar coordinates. There's technology that might incorporate polar coordinates a little bit better than what we do with our rectangular coordinates. If you guys know what like CNC routers and those kinds of things are, robotics might move and manipulate and work more efficiently using polar coordinates versus rectangular coordinates. Now, these two terms have been used in rectangular coordinates, polar coordinates. You guys are most familiar with, let's see here, with plotting points based off of the intersection of vertical and horizontal lines, right? So if I want to plot the point, let's just say 5, comma, let's do this. Let's go 4, comma 3. Okay, that'd be right there, right? It'd be the intersection of that line right there and that line right there, right? All right, now the way we move about and we get from our starting point, the origin, to that point A is that we move horizontally, we stop, and we move vertically, right? What kind of angle did I just create right there? Right angle, right? I could have done this. I could have gone up 3 and to the right 4. What kind of angles do I create here? Right angles, right? Okay. I could have gone right 1, up 2. Right 2 more, up 1, and then the right 1 more. Okay, my G is a little off. I could have done that. But what kind of angles do I make every time that I change direction? Make right angles. Okay? So that's why we refer to that as a rectangular coordinate system. When you're graphing X's and Y's, you're moving left and right and up and down, and that's it. Therefore, you're creating right angles. You're moving rectangularly. Does that make sense? Okay, so that's why that terminology is used. Now, if I want to get to that same exact point, there's another way I can do it. Okay? And those of you that have been to physics, you know that you can travel from B to A using that vector, right? Okay? Now that vector has a length, and that length right there is going to be whatever the radius of the circle that A is on. Does that make sense? So let me hide the lines. Okay? If I want to get to A from B using that vector, I'm going to figure out what circle A is on. And it's on the 5th circle, right? So that radius is 5. If I ask this thing for B to A's length, it's 5. Okay? Now, the other component that we need here is actually the angle in which we travel, 36.87 degrees. Does that make sense? Okay. Now I'm going to type in to GeoGebra a different way of finding point A. So let me first hide point A. All right, and see if what I type in puts me back at the tip of that arrow. We'll type in 5. Okay. Now, just to differentiate, that's not a rectangular system. GeoGebra requires a semicolon. Okay. So you go 5 comma. That 5 stands for the radius. And now the 36.87. So I think I can just ask it for alpha here. So that would be analogous to typing in 36.87 degrees right there for that second coordinate. Does that make sense? And when I hit enter, do you see where it put point D? Is that the exact same location that point A was? Okay. So we have two different ways of getting from B to D or to A there. Okay, it's that point. We can either go to the right 3 and then up 4, which is traveling how many units? I'll move to the right 3 and then up 4, that's 7 units, right? Or I can go from B straight to D by traveling 5 units at a 36.87 degree angle. All right? Which one's more efficient? The straight one, 36.87 degree one with a radius of 5, right? So if you've talked about in maybe a physics class, if there are forces pushing B to D, maybe I need 4 newtons to go this direction and then 3 newtons to go up, right? That's 7 total newtons. But if I want to push it in push B to D in a more efficient manner, then I just find the direction that I'm going to push it, 36.87 degrees, and I apply 5 newtons, and it gets me to the exact same spot. Okay? So that's kind of what you talked about in that class. Now, what you did in that class as well is that you took, okay, well, if I'm going to have a vector that has a magnitude of 5 and a direction of 36.87 degrees, how can I break that down to its horizontal and vertical components? The 3 and the 4 that we move left and right, up and down. And there, you got formulas for that, right? Those formulas that you were provided are going to be given to us today. Okay? And hopefully today you start saying, well, that's all we had to do. And I think usually in the past it kind of upsets people of how simple those formulas really are when we start understanding what polar graphs are, what polar coordinates are, and then how we're going to transition that into vectors. Now, this chapter is not about vectors. Okay, chapter 9 is about vectors. Chapter 8 is about polar coordinates, but without, I mean, they tie into each other. Okay. All right. So coordinate systems are used to locate the position of a point, location of a point in right now 2-dimensional space for us. It says in rectangular coordinates, we break up the plane into a grid of horizontal and vertical lines, and then you locate a point's position based on the intersection of one vertical line and one horizontal line, right? And what we call polar coordinates, you're going to start with a central point. Okay, we'll talk about what the vocabulary words for these things are as well. And then it's a series of concentric circles that are increasing by the same interval. That makes sense? So that first circle, and that innermost circle up on the right might have a radius of 1. Then the next circle outside of it is going to have a radius of 2. And then a radius of 3 and a radius of 4, right? So what we call these, I don't know if you guys remember this from geometry or not, but if I have a ring, now ring is not the math term. That's terrible. If I were to color in the region between 2 concentric circles, do we know the math word for that shape? Starts with an A. It's called an annulus. Okay. When we construct the polar coordinates, the polar grid, each annulus is the same width. Okay. Just something to think about as we move forward. Okay. Here you're seeing the way we describe points a little bit different. Okay. This one is saying that this point is called, and it's right here where my cursor is, it's called 4 comma pi over 6. 4 comma pi over 6. The 4 stands for the circle that the point is on. Okay? Essentially meaning how far away from what we call the pole, or it would be analogous to the origin, how far away from that you are, okay? And then at what angle measurement, whether it be in radians or degrees, okay? So that's kind of a breakdown of what rectangular coordinates are versus polar coordinates, okay? Now, the center of the graph, okay, which I said a moment ago was analogous to the origin in the rectangular system, right? That center we call the pole, okay? There's a lot of kind of parallel connections to the way we deal with lines of latitude, lines of longitude, and this stuff as well. Okay, if I were to make that pole my north pole or south pole and start folding that thing around a sphere, we start to get lines of latitude, lines of longitude, right? Okay. So we have that pole. Okay, the positive x-axis is referred to as your polar axis, and that is the axis that, or the portion of the axis that every measurement is based off of. Okay, it's just like what we've done with the unit circle. We always look at the positive x-axis and move counterclockwise, right? That's the same procedure here. All angles are going to be measured counterclockwise. Okay, points are represented by a radius and an angle. So they're going to be an r comma theta, where r represents what circle your point is on from the pole, okay, which ultimately tells you the distance that you are from the pole. And theta then is the angle in which you travel from the polar axis to get to that point. Now, these rays that emanate from the pole, so it's what pi over 12, pi over 6, pi over 4, we can start adding those. That's kind of like taking the x-axis and saying, I'm going to draw a vertical line through 1, 2, 3, 4, 5, 6. Or maybe I'll draw a vertical line through 1/2, 1, 1.5, 2, 2.5, 3, right? If we want rays emanating at the pi over 24 increments, we can do that. If we want rays emanating at the pi over 36 increments, we can do that, okay? A lot of times, those are the ones, though, that you see. That's kind of the most common polar graph setup right there. It's showing you the 15-degree increments, right? Okay. If you want put 360 of those in there, you have the 1-degree increments. By all means, you can do that. It's going to be messy. It's going to be a little cluttered and hard to interpret. But these are all obviously able to be adjusted. Okay. Same thing with the circles. Like I said, a lot of times we use the integer radii. So 1, 2, 3, 4, 5, 6. But if you want to go, you want to show 1.5, you want to show 2.5, you want to show thirds, 2/3, 3/3, 4/3, you can do that. Okay, you can adjust the circles and you can adjust the rays just like you adjust the x's and y's on a rectangular. All right, so your radius and your angle. All right, so here's how we plot these things. Now I'm going to show you a particular order, but you can actually jockey this order around. It doesn't matter. You know, if we graph, a lot of times when we graph an x comma y, we go in the x direction first and followed by the y direction, right? That's just that's the way it's presented in the order pair. So a lot of times that's the order we go. But you can go up and down first and then move left and right second, right? And get to the same location. That's kind of the idea here. You can either do what this says, and you can go out. It says first you're going to find the angle. So you can go out pi over 4 radians, okay? And basically what you do is you identify the ray or the vector that your point is going to be on, okay? So that pi over 4 tells me it's going to be on that solid orange line, okay? The next thing you do is you say, okay, well, I've got a distance of 5, meaning that I should be on, if these are all integer circles or integer radii, we should be on the 5th circle. Does that make sense? So we just, on that ray, count out to the intersection of that ray in the 5th circle. So 1, 2, 3, 4, 5. and that's our point. And we just plotted our first polar coordinate. Okay? Now, if you think about that, that is exactly the same thing as maybe finding the fifth circle. And then when you're on that fifth circle, move pi over 4 radians on it in the counterclockwise direction and get you the same location. Okay? Is that something we can do? Okay, find the angle and then count out what circle you're on for that angle. Okay? So a negative angle is going to be measured clockwise like usual. So I'm going to go 3 comma negative 3 pi over 4. So I'll find negative 3 pi over 4 first. So I'm going to travel that direction, negative 3 pi over 4 units, so it splits the third quadrant in half. It should be that ray, correct? Okay. Now I'm going to go out how many circles on that ray? 3 circles on that ray. 1, 2, 3, and there's my point. Now, here's my question. What's another angle for negative 3 pi over 4? 5 pi over 4. If I would have graphed 3 comma 5 pi over 4, does it give me the same point? Yes, it does. And that's the difference between some of the things that we do with rectangular systems and polar systems. In a rectangular system, this point 3 comma 1, there is one and only one way of identifying that location, right? In a polar system, if I want to find 5 comma, oh, where was that point? Okay. If I want to find 3 comma negative 3 pi over 4, there's an infinite number of ways of identifying that point. Okay? I'll just prove that to you real quick here with GeoGebra. Let's go. So we went 3, and then it was negative 3 pi over 4, right? Okay. What GeoGebra does is it will, initially, if you don't change any of the settings, it will put your theta in degrees for you. So that's, I think, a nice thing. I think I can go in to advanced. If you go radians, right there, yeah, it'll put radians, but it tells you then that it's in radians, right? So that's a nice thing, but I'm actually going to go back to degree. So 225 degrees. Now, if I would have typed in 3 comma 5 pi over 4, is it the same point? Yeah. If I would go 3 comma, let's go, so we started with negative 3 pi over 4, and I add to it 2 pi k. Now, why would I add 2 pi? It's because that's the coterminal angles, right? So you're going to be the same angle. And then k is going to be my integer that allows me to slide this thing. Let's go increments of 1 between negative 5 and 5. Okay, so we're looking at point C. Does point C ever move? No, but there's an equation here that's incorporating that k, right? Okay, so here, I don't know if it'll actually evaluate when I click it now. Let's do this. Let's try it this way. Let's say that t is equal to negative 135 plus 2 pi times k. So it gives me that thing there. Did I do that right? Negative 3 pi over 4. Okay. Is that doable? Okay, so that you're seeing it change there. So let's put this and write that as negative or 3 comma, and then we'll go t. And now, even though you see t changing, the point C, which is described by t, does not move, right? Okay. So this would be, so this here would be, this is radians. This is 3, and then negative 2.36 radians. So maybe I can do this. Maybe we can do it. Take that, and then multiply it by 180 over pi. So there we see, so now, well, that's messed up. Because that's got to be t degrees now. I think that'll fix it. There we go. Now you see that t changing from now 225. Now it would be really 585. Does that make sense? So 3 comma 585, 3 comma 945, 3 comma 1305. Those are all the same point, are they not? Okay. So that's kind of the. I don't know if you consider that a good thing, kind of a luxury for dealing with polar coordinates, because there's different ways of doing it, or you might consider that as kind of a bad thing, okay? Because there are, my neighbor might have something completely different than me, but we're both right, correct? And we've seen in the past where maybe with some of our work that can be a problem. But when we deal with measuring and locating coordinates for the polar system, there's more than one way of doing it. Here it says to plot a point with a negative radius. Okay, we can have that. Okay, a negative radius, the negative aspect does not mean that my circle does not exist. Okay, the radius of a circle can't be negative, right? Doesn't mean it doesn't exist. It's just providing me a direction. Okay, so when I want to graph that point right there, -4 comma 2 pi over 3. You're going to do the same thing first. You're going to graph out 2 pi over 3. And this is the reason why at the beginning in plotting these, they tell you to do the degree first, or the radian first, theta, your angle, because what happens when you have a negative radius? We're going to plot out 2 pi over 3. We're going to find that vector. Okay? Now, if this was 4 comma 2 pi over 3, you'd go out 4 on that radius, or that vector, right? Okay? Well, now it's -4. So what you do is you find the opposite ray. The opposite ray is the ray that is going to be, that will form 180 degrees with the current ray. Does that make sense? Okay, so I go across the pool, okay, or I reflect that solid 2 pi over 3 vector across the pool 180 degrees, and then I count out 4 units on that vector. Does that make sense? Okay. Usually people struggle with that -1 because of the problems that we see. We might see, 20 positive radii and maybe 3 negative radii. So just the amount that we see of them can kind of maybe hamper us a little bit. Okay. So if I want to go 7 comma pi over 2. First find pi over 2, and then I count out 7 circles, right? Pretty straightforward. Okay. Well, what if I wanted to graph that point right there? -7 comma negative pi over 2. Find negative pi over 2, right? Negative pi over 2 is going to be that angle right there, correct? Well, if it's that angle right there, then the -7 tells me to find the opposite ray, correct? So the opposite ray of negative pi over 2 would be positive pi over 2. Okay? And now I count 7 units on that, and it gives me that point there. Are they the same point? Yeah. Same exact location, 2 different ways of determining it. Let's do this one. 7 comma 5 pi over 2. 5 pi over 2, how many times around the unit circle is that? 1 1/4. Okay? 4 pi over 2 would be 1 time around, right? 4 pi over 2 would be 1 time around, and then pi over 2 more would be 5 pi over 2. And I'll count 7 units out on that ray, and it gives me that point. Same point, right? Okay, so it's just kind of a procedure. So if I go 7 comma -3 pi over 2. -3 pi over 2, sending is pi over 2. And I count 7 units out on that one, and you're going to get the exact same point. Okay? Now, the only thing that I can do for the radius is either keep it 7 or -7. Does that make sense? Okay? Now, the things I can do for theta then are either to take theta, okay, and keep adding 2 pi to it, or subtracting 2 pi from it, right? And that will get me the other versions. Now, so that yellow one is keeping 7 positive and then going from that yellow one to the green one, I just added 2 pi, right? Okay. Now, if I look at the blue one, it's negative 7 comma negative pi over 2. So what I did there is I took the 7 pi over 2. I knew where that point was, and I just negated the radius. Okay. Well, if I negate the radius, I should probably negate the degree or the radian as well, so that I can get to the same location. Does that make sense? Now, if I take that ordered pair, negative 7 comma negative pi over 2, and I either add or subtract 2 pi to that, I will get another set of infinite values. Okay. The purple one is taking the yellow one and subtracting 2 pi. Okay. I don't have any up there that use that blue one by subtracting or adding 2 pi. But, you know, if you wanted to add, so if you went negative 7 comma 3 pi over 2, that would give me the same point right here, right? Okay. So that's kind of the procedure of developing additional versions of the exact same point. A lot of times, guys, the practice is to let our radius be positive. That's what we usually want, a positive radius, and then the smallest theta that we can use, smallest positive theta that we can use. Does that make sense? And that's usually the, like on a test or a quiz, so that I don't have to judge, because we could legitimately have 35 different answers, right? 35 people in the class. Instead of having to judge, see each one of those is correct, what I'll do is I'll write it, say, make sure your R is positive and that it's between 0 and 2 pi. All right, or 0 and 360. We can go from there. Okay? All right. So now the part that becomes very, very, very useful for us. If you look up there on the board, on the whiteboard, it says 3 plus 4i raised to the 1,000th power. Okay? If you guys remember back to college algebra, we took 3 plus 4i, complex number, right? And we squared it, we cubed it, we did all that kind of stuff. We ended up getting I squared and that kind of stuff and making it into -1 and condensing it and evaluating everything, okay? We haven't talked about how to graph 3 plus 4i. It's a complex number. We need a complex plane. We haven't talked about that yet, but we're getting there. We're getting closer to that. But this process of working with polar coordinates, it would actually allow us to take 3 plus 4i raised to the 1,000th power and do that algebra extremely quickly, okay, almost instantaneously, okay, to where if I was doing it using our traditional rectangular coordinates, I would have to take 3 plus 4i and multiply it by itself, right, see what that gives me, and then raise that to the 500th power, right, and then maybe I take that thing and I square it, okay, and raise that to the 250th power. And I can keep doing that, but and then that process of raising to the 1,000th power, then the 500th, and then 250, and the 125th, is going to allow me to kind of cut down the amount of factor or foiling that I have to do, but it's still an immense amount of foiling that I want to do, okay? Even if I was just to the 10th power, even the 3rd power or 4th power, what we're going to find out is that rectangular coordinates convert into polar coordinates. Once you convert it into polar coordinates, that process raising to a large power becomes very, very quick, okay? And a lot of like computer programming and stuff like that, what we're interested in is saving RAM, saving memory, applicable memory or accessible memory, okay? So that my computer program doesn't stop, right, or slow down. So what we do is we write code so that takes maybe polar coordinate or rectangular coordinates and transverses them into polar, does the math with them that way, and then kicks it back into rectangular when we're done. Okay. The way you move a mouse across the board, okay, across the screen, uses vectors. Okay. There's vector fields and all that kind of stuff at play. And I don't know what the code is for that, but perhaps it uses some of that polar coordinate stuff. Okay, so if I want to take 3, 4, I want to talk about how I get 3, 4 into polar coordinates. We first have to do this. We have to draw our radii from the origin to that point. Okay. Now, this is analogous to what we did in the first week of geometry 2 years ago. We're going to find that distance. Any point located in the coordinate plane, you can find the distance. And if we're going to do it from the origin, it's really nice because one of your points is 0, 0. To use the distance formula, I should be able to find that R value, right? Well, the distance formula is just what theorem? Pythagorean theorem. So I want to find r, because that's what my polar coordinate is going to be defined as. I'm going to take 3 squared plus 4 squared equals r squared. So r ends up being what? 5. Okay. So r ends up being 5. Okay. So now that I have all 3 of those dimensions, and I want to find theta, okay, you're going to use sine, cosine, tangent, inverses, right? Now here's the thing. You can use any one of those. But most of the time, that r value is not going to be a real friendly number like it is right now. Okay? Might have radicals with it, that kind of stuff. Might have to be a number that you rounded or whatever. The numbers that we do know, though, are 3 and 4, right? Those numbers are concise, they're exact, and they are, for theta, the opposite and the adjacent, are they not? Okay, so the best trig function to use is the tangent. The tangent of theta is equal to 4 over 3 in this case. If I evaluate that, we'll do it in radians, it gives me 0.93 radians. 0.93 radians. Okay, so then we got our r, and we got our theta. So we write our answer, polar coordinates, are 5, 0.93. Okay, now that looks eerily similar to a rectangular system set of ordered pairs, right? Okay, because there is no degree symbol there. So there's nothing to kind of allow us to differentiate that is supposed to be polar coordinates versus rectangular. So you can do a couple things. If you could do what GeoGebra does, and they put a semicolon. So that allows me to differentiate between polar and rectangular. I don't know if that's I haven't seen that in other textbooks. Okay, I took complex analysis in grad school. That's all that class is about, is polar coordinates and circles and A plus BI stuff and how that all kind of intertwines and interrelates. So we do a lot of this in that class. It never showed that notation. Okay, if you want, I don't care if you use it, but I don't think it's an accepted notation across mathematics. Does that make sense? What you can do additionally is you could write 5, 0.93 and then just put RAD in there, okay? Or just leave it at 5.0 or 5, 0.93 and just know that it's radians. Does that make sense? And just kind of keep track of things in your mind like that. That's fun. But a lot of times people get confused. Was that radians? Was that is that a y value or what? Okay, so that's something to think about. Now, if that actually works, then we should be able to look at our graph here. Okay, if I put on here, so we started. I'll just put the grid back as this one. We started with the point. Was it 3, 4? Or was it 4, 3? 3, 4? Okay. So 3, 4, we got that point right there, right? We just found that we're going to rewrite it as 5, now, it was 0.93, but that's rounded. I'm just going to use arctangent of 4/3, so it's not rounded. If I plot that, did it put it on the same exact spot? Okay, so that blue X is on the same as the red circle, right? The red dot. So it's the same point. But now we see with changing the grid then back to polar that you are indeed on the x squared plus y squared equals 25. You're on the 5th circle, right? Okay. And if we were to figure out how many radians that is, it's going to be, well, let's just do this. Let's go in degrees. We go there, 53.13 degrees. Does that make sense to everybody? Okay. So there are some ways of checking using technology that you've done things correctly. And that thing I drew on there about an hour ago, and it just wants to pop up. All right, so let's actually we can do this. All right. All right, so let's generalize that process, okay? Because we don't want to have to draw a picture every time we do one of these, okay? So we're going to be given a point x comma y. Okay, that's going to be r, that's going to be theta, that's going to be y, that's going to be x, right? Okay? If I want to find r using the x and y I know, then it's just solving that Pythagorean theorem question, right? For r. So your radius is always the square root of x squared plus y squared. Theta is always found by using this relationship. The tangent of theta is y over x. And then theta is equal to tangent inverse of y over x. If you remember back to like a physics class when we talk about vectors, you were often told, okay, I am moving this particular, I'm applying a force to this object at the origin, and I'm going to apply a horizontal force of 3 newtons. And we'll apply a vertical force of 4 newtons. Okay? And you're asked then, how many newtons was that? 7 total newtons, correct? And then they say, okay, what's a more efficient way? The more efficient way is to go from the origin straight to where x comma y is, right? Go along that radius. And this is the way that you would have found the length or the magnitude of that vector and the direction of that vector. You guys remember? Okay? It's the exact same stuff we're doing here. Okay? And they gave you these formulas in physics. Now, it might not have been x and y they used. They might have used a and b. They might have used, like they put like absolute value symbol around a v for the vector instead of r, but it's the same thing. Okay? They might have even used z. Okay? They use C and S stuff. Kind of go off from memory. We'll get to seeing some examples of the information you did in that class, but there's a direct link between physics and trig in college algebra. Okay. All right. So now let's do it the other way. Let's if we can go from rectangular to polar, we should be able to flip the script and go polar to rectangular. I think this is much easier, much quicker. Okay. So this is based on the trig. You can see how we can come up with y and x, okay? This angle in here is pi over 4, okay? So what we can do is say that the cosine of pi over 4 is equal to cosine is adjacent divided by hypotenuse, right? Adjacent is my x value. My hypotenuse I know to be 4. That's my radius, okay? So then multiply that out, multiply both sides by 4, and evaluate the cosine of pi over 4. Cosine of pi over 4 is the radical 2 over 2, right? And multiply both sides by 4, that would isolate x. And I get 2 root 2. So that's my x value. Do the same thing for the y value. Sine of pi over 4 is opposite over hypotenuse. So y over 4 in this case. Multiply both sides by 4, you get 4 sine of pi over 4. The sine of pi over 4 is radical 2 over 2 again. Pair 2 root 2 comma 2 root 2, and that yellow order pair is now the rectangular coordinates to get the 4 comma pi over 4. You guys remember talking about in vectors breaking something down to its horizontal and vertical components? That is that process. We just broke down that vector from 0 to 4 comma pi over 4 down to the horizontal and vertical distances that we can use to get there instead. All right, so how do we generalize that? And this is where maybe some of your physics formulas are going to show up. We saw with r comma theta. We draw in that right triangle. Well, that's r, that's y, that's x, that's theta. And every single time, you're going to say, well, cosine of theta from 9th grade geometry is a hypotenuse, right? But as we're doing these, we want a formula that just gives us x every single time, instantaneously. So we multiply both sides by r, and we get that formula. Then we do the same thing for sine. Sine is opposite over hypotenuse. But we want a formula that always gives me y instantaneously. So y equals r sine theta. Multiply both sides by r. So those yellow ones are the formulas you're probably given in physics, which probably weren't showing where they came from, why you got that r out front. It's SOHCAHTOA from 9th grade, 10th grade geometry. Okay. So what happens then is, instead of having to draw these pictures every single time, we want to do something like this. We want to take that point and let's put that into rectangular form. It's in polar right now. It's got a good degree with it, right? So if I want to go into rectangular, I got to find x. X is r cosine theta. The way I remember these, x comes first alphabetically, right? Cosine with sine. So x and c go together. Y, or if you just think about it, you're in a circle. X and cosine, y and sine go together, right? So now what is r? 8. So we go 8 cosine 210. And down here we go 8 sine of 210. So what is 8? Well, what's cosine? Negative root 3 over 2. So we got 8 times negative root 3 over 2. And what is the sine of 210? Negative 1/2. So we got 8 times negative 1/2. Ignore that green thing that popped up. So I get then my x value. If I multiply this out, it gives me negative 4 root 3, right? And then my y value, multiply that out, gives me. So this point right here, that's like the 8th circle there at 210. If you were to travel that distance, negative 4 root 3, and then down 4 units, it gets you to the same spot. Okay? So that's how you convert from polar to rectangular. There's an assignment on WebAssign for 8-1 due on Wednesday. Where we're taking this stuff to give you kind of a picture of what some of this stuff looks like. This is one of the things that we're going to be interested in doing. Like I might be able to say like 3r, or 3, let's go, sine of 4 theta. We might graph something like that. Okay? And we start doing, there's a lot of things that you can do to these things.
Students, this is a reminder that all students are to report to their original Wildcat Time teachers this week, near future, until further notice. Again, everybody report to the original Wildcat Time teachers. Also, the Lima Police Department Summer Academy meeting will be taking place in the high school lobby during Wildcat Time today, for those interested. Thank you.
So there's a lot of different weird things we can do with these polar coordinates.